Study of diode, clipping and clamping circuit. In electronics, a clipper is a device designed to prevent the output of a circuit from exceeding a predetermined voltage level without distorting the remaining part of the applied waveform. Whereas a clamper is an electronic circuit that fixes either the positive or negative peak excursions of a signal to a defined value by shifting its decibel. So this is the objective of this experiment, Nipper circuit and Clumper circuit. So I will take you to a web page to go through this topic in details. Clipper, sometimes called limiting circuit. Clipping circuits are used to select for transmission that part of an arbitrary waveform which lies above or below some reference level. Clipping circuits are also referred as voltage or current limiters, amplitude selectors, or slicers. So this is the objective, to study the behavior of clipping circuit for following cases. Main scenario, clipper circuit with diode in series. There are two cases. Case 1, clipper circuit. Okay, clipper circuit. Case 1 is clipper circuit with forward biased diode in series. And case 2, clipper circuit with reverse biased diode in series. Then again, clipper circuit with diode in shunt. In that case again, two cases. Case 3, clipper circuit with forward biased diode in shunt. And case 4, clipper circuit with reverse biased diode in shunt. Third scenario, clipping at two different levels. That's case 5, clipper circuit with limiting at two different levels. So 5 cases we are going to investigate under this clipper circuit. So this is the theory. You need to understand it properly before we do the lab. Clipper circuit with diodes in series. The case 1. The clipper circuit with diode in series has two cases, such as diode connected in forward bias and in reverse bias. Case 1. This is the case 1. Okay, clipper circuit with forward bias diode in series. Look at over here. This is the input voltage, AC voltage. This is the diode, anode, cathode. Look at over here. This is reference voltage. VR is the reference voltage, and it is forward biasing the diode. Okay, so the clipper circuit has a forward bias diode D. This is the forward bias diode D in series with a reference voltage in shunt. This is the reference voltage VR in shunt as shown in the figure. At the output, we measure the voltage at this two terminal. This is the output voltage. So what happens in this case? Look at over here. If the input voltage Vi, this input Vi is greater than VR, okay, then the diode D is in forward bias, means on state. If this input voltage Vi greater than VR reference voltage, then certainly this diode will be in forward bias on state. The output state will be same as V input. When this is forward biased, at the same voltage that you apply to the input, you will get at the output. The transfer curve has one breakpoint when V output equal to V input equal to V reference voltage and has the following characteristic. Assuming reference voltage much more greater than the diode internal voltage, okay, and forward resistance RF, this resistance is much lower than that forward resistance is much lower than this load resistance. So this is the scenario when input voltage is greater than the reference voltage, okay, diode is on. Input voltage is greater than the reference voltage, then diode is on. In this case, when the diode is on, we get the same voltage output that we apply at the input. But when input voltage is less than or equal to reference voltage, diode is off. In that case, VO equal to VR. That means when VI is less than or equal to VR. Okay, you can think about it. It's less than or equal to. If it is equal, listen, they get this. I think reverse biased. Okay, this get reverse biased, and that become off. When that become off, nothing comes. So this portion you don't see at the output. So that portion get clicked. When diode is off, in this case, look at over here. When diode is off, that portion get clicked. When the diode will get off, when Vi is less than or equal to VR, then the diode will get off and it will remove that portion from the input or applied voltage. Let's see with the picture. This is the input signal Vi, okay, and this is the output signal Vo, and this is the reference voltage VR. When Vi equal to less than or equal to VR, D is off. When input voltage, that means this voltage, input voltage B is less than or equal to V, this voltage, then diode is off and nothing conducts. Look at over here. This voltage is less than or equal to reference voltage. Then diode is off and nothing conducts. So if you overimpose those two pictures, look at over here. This is the reference voltage. This is the reference voltage. Okay. When diode is on, only you get this portion. This is the on state. And when the diode is off, this portion from the input wave get cut down. Okay. And it depends on the reference voltage. At the reference voltage, when Vi is, look at over here, less than or equal to VR, diode is off. So you don't get the shape of the output. So when Vi, this input voltage less than or equal to V reference voltage, at this region the diode is off. So you don't get this portion of the output. Only you get the portion when the diode is on. That means when Vi greater than or equal to reference voltage. When the input voltage is greater than or equal to reference voltage, then diode is on and you get that portion of the output. So what is happening? You are clipping this portion. Okay. So this is the one case one. Next case, clipper circuit with reverse bias diode in series. So this is the reverse bias diode in series. Okay. This is reverse biased. You see, negative terminal, positive. So it is reverse biased. If input voltage Vi is less, opposite scenario we'll see over here. If input voltage Vi is less than VR, then the diode D is in forward bias on state. Just opposite scenario than the previous one. The output voltage Vo equal to Vi. So what happens when Vi is less than VR? Diode is on state. Otherwise, diode is off state. Look over here. Vi less than equal to VR. This VR is the reference voltage. Then diode is on state. So look at the scenario. Vi, this is the input voltage, input wave shape. Input wave shape, and this is the output wave shape. And this is the reference voltage. When Vi less than VR, okay, that means when this input voltage will be less than VR, then diode is on, and this portion is at the output. Otherwise, diode is off. This top portion does not appear. Cut down. Clip. So what you see? Finally, you see blue color portion is clipped, and this is the output. Okay. Yellow color. This is the, or I think orange color is this the output. This is the output. Here. Just opposite scenario than the previous one. Case one. Now case three. Clipper circuit with diode in shunt. This is the diode in shunt with the reference input voltage and series with the reference voltage. If input voltage Vi less than VR, then diode D in forward bias means on state at the output we get Vi. Otherwise, that is off state. Okay, so we are interested in the on state. When the diode is on the on state, that portion will not appear over here. Look at over here. When the diode is on state, it will conduct, and that portion will not be at the output. But when the diode is on off state, just opposite case than the case 1 and case 2. When the diode shunt, just opposite case of series, when the diode will be off, that means it will not conduct. When the diode doesn't conduct, you see the input and the output. Just opposite scenario of the series case, okay? Case 1 and case 2. So over here we'll consider the off state. At the off state of diode, we will see the output. Okay? So when the off state, Vi less than Vr. This is Vi, this is Vr. Vi is less than Vr. This is the reference voltage Vr, and this is the Vi. Vi is less than Vr. So diode is off. Diode is off. You see? Diode is off. In that case, the input, this portion, blue color portion will appear at the output. Because diode is off, so it cannot conduct, and we get the input at the output. Okay, this blue color portion. Okay, so what you see over here, we are clipping this peak. Okay, and this orange color portion is coming at the output. Just opposite case of our series case. Okay, case 4 again. The clipper circuit with reverse bias diode in shunt. Okay, this is the case 4. Again, just opposite scenario of the case 3. Opposite scenario, that means over here only we will see the peak. Opposite scenario. So we are interested on the off state of the diode. When the diode is off, Vi greater than Vr. When input voltage is greater than reference voltage, diode is the off state. So this is the input voltage, and this is the reference voltage. So input voltage is greater than reference voltage. At this region, the diode is off, so we are getting the we are getting this at the output because diode is off. Okay, at this region, when the diode is off, that means diode is off at this peak. So this orange color portion we are getting at the output because diode is off at that time. Okay. Now, last case, clipping at two different. This is the combination, okay, of case 3 and case 4. So in case 3, what you have got? Case 3 and case 4. Case 3, what you have got? Case 3. I think over here we'll get only one portion, two peak. Okay, let's see. Let's analyze it. So clipper circuit with limiting at two different levels. Diodes may be used in pairs to perform double-ended limiting at independent levels. A parallel series or series parallel arrangement can be used. A parallel arrangement is shown in the circuit B. So this is the reference voltage 1. This is the reference voltage 2. This reference voltage 2 must be greater than reference voltage 1. Okay, in this case. The transfer curve has two breakpoints, one at VO equal to VI equal to VR1. VO equal to VI equal to VR1. When VI equal to VR1, this is one breakpoint. And the second one, when VO equal to VI, that means when VI is equal to V reference voltage 2. So when VI is equal to V reference voltage 1, one breakpoint. When VI is equal to reference voltage VR2, another breakpoint. Okay, so why we are interested? We are interested in the two off state. First off state, okay, that means when this will be the off state, this will be the on state. Okay, and when the let's analyze. So one scenario is the B I equal to B reference voltage 1. D1 is on. When D1 is on, Okay, then D2 is off. So D1 is on, that means it is conducting, D2 is off. So you will get this voltage at the output, one reference voltage. That means it will one will conduct, another will not conduct. Okay. So this is the input Vi. The output signal VO is shown over here. Okay. So what is happening? The input output signal together with Vi or VO is shown over here. Okay. So we are interested in these two situations, I think. VO equal to VR1, VO equal to VR2. So when VO equal to VR1, okay, D1 is on. This D1 is on, and D2 is off. D1 is on and D2 is off. So it is cut down. You can remove it, and D1 is, this is on. Okay. So what you will get at the output? This is on and D2 off. Okay. So what we are going to get? D2 is off, means it will not conduct, cut down, and this will conduct. So when this conduct, and Vi equal to VR, so what you get? You get some voltage that is greater than VR. Okay, that is greater than VR. That means this is the reference voltage. This is conduct. Okay, when this conduct, that means that things that would conduct, that is Vi, that is above VR, that will conduct. But Vi that is less than VR, it will not conduct. So look at over here. Vi that is less than this reference voltage will not conduct at that time. But when Vi is greater than VR, that portion will not conduct. Vi greater than VR, okay, that portion will not conduct. But when Vi is less than VR, that portion will conduct. You see, Vi less than VR, D1 is on, that portion will conduct. Okay, so the portion that does not conduct, it will appear at the output. So this portion does not conduct, okay, that will appear at the output. For the second case, okay, when input voltage is equal to the VR2 reference voltage, D1 is off, just opposite scenario, D1 is off and D2 is on. When D2 is on, look at over here, then this portion that is above input, the portion that is above the input of the reference voltage, that is not going to conduct, okay. That is going to conduct, but the portion that is below, that is in this range, the portion that is in this range, the VOI, that means input voltage is less than the reference voltage, that portion is appearing at the output because diode is off at that time. Okay, diode is off at the time, so that portion will appear at the output. We'll approve these things for experiment. Okay, we'll do the experiment and we'll prove all the scenario step by step. So let's go to the next part. There's a small pre-quiz we'll take. Clipping circuit are also referred as voltage or current. Fourth choice. Which one is true? Clipping circuit are also referred as voltage or current. One option is a limiter, amplitude selector, slicers, all of the above. Which one is true? Clipper circuit can be limiter, it can be amplitude selector, it can be slicer. So what do you think? Give me some feedback. Which one is true? Yes? Which one is true? Yes, all the is true. When you see it is right, it is green color. And if you select the wrong one, okay, it will be the red color, okay, other color. So this is true. Next. In clipper circuit, the diode can be used in reverse or forward biased, series or shunt. Reverse biased, second option is a reverse biased shunt. Third option reverse biased series. Fourth option reverse biased shunt. So what do you think? Which option is true? 1, 2, 3, and 4. What you have seen from the theory? Yes. Let's pick up one. Green. It's true. The clipper circuit can clip at two different levels. True or false? True, right? Because we have seen on the case 5. At two different levels, it is clipping. Yes. So, we have successfully passed the pre-quiz. Now is the simulation. 5 option for the 5 simulation. First option. Clipper circuit with forward bias diode in series. What I suggest, as I do, all of you do the same thing on your computer, because this is the lab you are doing by yourself practically. That means this is, you can imagine this is your physical laboratory. So all of you open up your browser, make sure you come to this simulation part. When you are done, tell me. I'll go to the simulation. So open up your browser, go to the simulation part. Are you there? Okay. Now click it. Now you see instruction. Observe the circuit diagram of the clipper. Click on the power button. Then select the amplitude of the input sine wave Vi. Then select the frequency or RF of the input signal Vi. Okay. Then select the battery voltage, reference voltage. This is VR. Observe the input signal and clip output signal in the graph. Change the value A, F, and VR to observe the variation in the output signal. Hover the graph to observe the value of the Vi and Vo at the instant of time t. Save the graph if you are done with your experiment. Now there's a point. Make sure always this VR reference voltage must be less than or equal to amplitude A of the input Vi. From our theory, you know that this must be always less than. Otherwise, it will not do the clipping. Okay. it cannot do the clipping unless VR is less than or equal to amplitude of the input sine of signal, Vi. We take the amplitude. Okay, so these are the steps, instructions. So this is the circuit. You see, the diode, the clippers with forward bias diode in series. Okay, case 1, let's apply the power. Click the power button. Power on. So this is the oscilloscope. This is your circuit. This is the function generator control. Voltage and frequency. Okay, same function generator that you use in your physical laboratory. And this is the reference voltage for the battery. You can, let's say, is DC voltage, I think, a supplier, variable DC voltage supplier. Okay, these are the physical equipment that you use in the actual lab. Okay, now this is the oscilloscope, channel 1 and channel 2. Similar we perform in the actual lab. This is the voltage per division, millisecond per division, and this is the position of your curve. Okay, second, for similarly for channel 2, voltage per division, time per division. Okay, and this is the dual view. Okay, so let's start the experiment. Look at over here, 5 volt. However, you take your mouse and use your mouse wheel to change the value. Take the mouse over the knob and move your mouse wheel forward or reverse direction to change the value. Okay, let's say take 5 volt at the beginning, for example, amplitude 5 volt, Vi, frequency is 5 kilohertz, you can change it if you like. Okay, let's say 3 kilohertz, for example. Now, the condition we need to meet, this Vi must be greater than VR. You see, this is the condition from your instruction. Reference must be less than or equal to amplitude of the input voltage. Okay, so this Vi must be greater than or equal to VR. So this 10 value is wrong. We cannot take 10. It must be less than or equal to Vi. So take your mouse. Yes, any value 5 and below allowed. Okay, 5 and below allowed. What happens if you take greater value? Let's see. It will not click anything. Okay, let's take a greater value. Let's say take 6 volt. Okay, this reference volt is greater than the input volt, greater value. So you see no clipping. Okay, let's see the view on channel 1. Channel 2, no clipping. 1. You see, this is the reference voltage and no clipping happening. So what thing we need to do? This battery voltage reference must be less than the amplitude of the input voltage. So let's make it 5 equal. Just even it is not clipping because just on the margin on the top. So what we need to do? We need to make it less. 4 or 3. If we make 4, look at over here. Make the same frequency of both channel. Okay. If you look at over here, this is channel 1. We have given volts per division, 3 volt per division. Okay. Let's give 1 volt per division. Channel 1. Frequency 2 millisecond per division. Similar on channel 2. Make 1 volt per division. Same as channel 1 so that we can compare. And 2 millisecond per division. Now let's see channel 2 and this dual value. So look at over here. At what level we are getting clipping? At voltage reference voltage level 4. This is the value 4. Look at over here. This is 4. At the value 4, we are getting the clipping. That is orange color. That's our clipped output. That's our output. So at the reference voltage 4, we are getting clipping. If we reduce the reference voltage 3, 5, 2. At reference voltage 2, we are getting the clipping. Let's make it 1. At reference voltage 1, we are getting clipping. If we make reference voltage 0, You see, we'll get the entire positive cycle clipped. Okay, the half wave rectifier circuit. It is half wave rectifier circuit. Okay, so you see, by changing the reference voltage, what we see, by changing the reference voltage at different level, we are getting the clipping. Okay, so that's so you can then fine tune at what level you want the clip, accordingly set the reference voltage. Okay, so have you done? Okay, take your mouse on top of the knob and use the mouse wheel. Just forward direction will increase, reverse direction of the wheel will decrease the value. I am just taking my mouse on the knob, then I am using the mouse wheel to increase and decrease the value. If I move the mouse in forward direction, value get increased. If I move the mouse in reverse direction, value get decreased. And what I have done for the oscilloscope, both channel 1 and channel 2 on the same, I think, reading. Okay, that means same setting. Volts per division, millicent per division, we have kept the setting same so that we can visualize the curve nicely on one on top of other on the same scaling. And now if you just move your mouse pointer over the curve, you can measure the voltage. At what level, what is the voltage, you can measure. Just hover the mouse over the curve. All of you have successfully finished the experiment. Change the frequency, change the amplitude, and verify the theory. That's your experiment. Case 1. So this is the same way you perform the experiment in the real physical lab, okay? Same way. So have you tested again? Let me increase the reference voltage and the input voltage. No clipping. You see, reference voltage is this one, yellow color, orange color, blue color is the input voltage. No clipping. Now make the reference voltage less than the input voltage. So at the voltage level, at the reference voltage level, you are getting clipping. So according to just vary the reference voltage at different point, we'll get the clipping. Okay, orange color part is your clipped wave shape. Make sure both channel 1 and channel 2 settings should be same, like volts per division, time per division should be same. So are you done? Can I power off this first case? Similar way, we'll test all other scenario. Let's power it off. Now we'll go to the case 2. Clipper circuit with reverse bias diode in series. Case 2. Is in this case VR less than or equal to amplitude. Okay, let's power on the circuit. Over here we are getting the opposite things. Okay, this is our, I think, amplitude Vi 8 volt. Okay, and this is the VR. VR must be less than or equal to V I. Okay, so in that case, what we are getting? We are getting the opposite of the case 1. That means if you look at the channel 2, this is the clipped output. Dual wave, this is the orange color portion that you are getting the output. Okay, so you are clipping some more parts, or you are just removing the peak of the shape. Okay, and you are getting this portion, yellow color portion, you are getting the output. That's the case 2. Case 3, clipper circuit with forward bias diode in shunt. In this case, only the situation condition, make sure always BR less than or equal to A. As before, you see this is clipper circuit with forward bias diode in shunt. So let's power it on. Okay. Again, what we are getting in case 3? This is our input voltage 5 volt. This is our reference voltage. So what is happening over here? The peaks of the input option are getting clipped. So we are getting the bottom part. Orange color part, we are getting the output. Yes, you can just take the screenshot. Just take the screenshot. No, it will be, you can do it, work with any time. It is free to use, okay? No restriction. No, this time I was showing just our time. That means this is the present time, 3:16 is the present time in our area, in Dhaka, and we are using this space for 53 minutes 23 seconds, almost close to an hour. So let's go to the case number 4. You can work with this simulation anytime. Let's power it on and make sure VR less than or equal to A, okay, as before. So this is the circuit, clipper circuit with reverse bias diode in shunt. Okay, so again, I think channel 1, this is the input voltage. Channel 2, what we are getting? This is our output we are getting, and dual wave. I think it has been shifted, so let me just bring on the same place. So you can change. It's like in the real oscilloscope, the things you do, similar way you can change in the real oscilloscope. Okay. Exactly same thing that you do in the real one physical lab. So finally, what you are getting over here, the orange color portion is your clip output. This is the orange color portion, and you can change the orange color portion by changing the reference voltage. If you give less reference voltage, more output you will get. Okay, more portion of the output you get. Yeah. So you can play with it, okay? Vary the input voltage, vary the reference voltage, and see how you are getting the output. So this is case number 4. Now case number 5. Look at over here. Two conditions. Make sure reference voltage VR1 is less than or equal to A and VR2 greater than or equal to VR1. This condition must be met over here. VR1 less than or equal to A. Okay, reference voltage 1 must be less than or equal to input voltage magnitude A, and reference voltage 2 should be greater than VR1. Okay, let's power it on. Okay, so this is VI 7 volt, reference voltage this one, and this is VR2. What is the condition? VR2 must be greater than VR1. So, okay, VR1 should be less than VR2. Select VR1 value properly. Okay, so so VR1 should be less than VR2. Okay, so what we need to do? We need to increase this one. So I think better I think power it off and do it again. So we'll adjust it. Okay, better power it off, then adjust, then we can I think it will work properly. Power it off. Now I think refresh the circuit simulation. Okay, now power it on. Now I think do it properly. Okay, you see the condition is VR1 less than or equal to VA and VR2 greater than VR1. So let's change it. 5 volt. If I pick, this should be less than VR1. You see VR2 greater than VR1. So you need to keep VR2 greater than VR1. I think it is okay now. You see it is -3 and this is let's say -2, -1 or 2, -1. So VR1 now less than VR2. Okay, so this is channel 1, the input voltage, output, and this is dual. So this portion you are getting clipped. Okay, you can change it by changing the value. This should be greater than. It depends. Okay, how you with the amplitude. Yeah. So that's the orange color is your output. clipped at two different sides. You see, you're getting clipping on the top. This portion, yeah, I think blue color, and at the bottom blue color. Only you're getting some part in the middle. Okay, and you can change the value by changing this value. Okay, just vary the value, and you can see how at what portion you are getting clipped. That is, by varying the value, you can find out this orange color portion you are getting clipped. Okay, just change it. You see, the area that you are clipping is varying according to your reference voltage. Okay. So you perform this lamp, and once you are done, you can go to the next part. So post quiz. Identify the below clipping circuit. Four option. Which one is true? Tell me. Option 1, 2, 3, and 4. Which type of circuit it is? Clipper circuit forward bus diode in series. Yes, very good. Next. Clipper circuit with forward bus diode in shunt is shown below. If Vi is less than VR, the state of the diode is on. No. Off. Off is true. It is green color. You can verify through the simulation, okay? So, next. Identify the input Vi and output Vo curve for the given circuit below. Which curve is true? This is, I think, double-ended clipper. Clipping at two different sides. Just like case 5. This is case 5. 4 curve. First option. This is only one side clipping. Second option, one side clipping. Only one side clipping. Both side clipping. So looks like this is the right candidate. Can I click this one? Yes. So you have passed the test. So clipper circuit portion is complete. Our next step, we will go to the clamper circuit. So this is the clamper circuit introduction. A clamper circuit can be defined as a circuit that shifts the waveform to a desired reference DC level without changing the actual appearance of the input signal. Okay. As the DC level gets shifted, a clamper circuit is also called as a level shifter. A clamper circuit adds an input AC signal with a DC level. Using the clamping circuit, the peaks, that means positive peak and negative peak of the signals, can be placed at the desired level. Clamper circuits consist of energy storage elements like capacitors. A simple clamper circuit comprises of a capacitor, a diode, a resistor, and a DC battery if required. So let's see the objective. Again, there are 6 cases. In this case, case 1, positive clamper. Case 2, positive clamper with positive reference level here. Case 3, positive clamper with negative reference level. Case 4 is the negative clamper. That means negative clamper means on the negative side you do the clamping. Positive clamper means on the positive side you do the clamping. Negative clamper, on the negative side of the magnitude you do the clamping. So again, there are 2 other cases: negative clamper with positive reference level and negative clumper with negative reference level. So let's go the theory one by one. Case 1, positive clumper. When a negative peak of the signal is clumped above the zero, then the signal is said to be positively clumped, and the circuit is called positively clumper circuit. So what do you expect? The negative peak of the signal is clumped up to the zero. So look at over here. If this is an input signal, we want that negative peak. This negative peak will be shifted above zero. That is the positive clumper. Look at over the arrangement. A positive clumper consists of a capacitor in series, reverse bias diode in shunt, a resistor R in shunt, as shown in the figure. So this is the positive clumper circuit. Initially, the capacitor is not charged in positive half cycle. Okay, and the diode is in off state. In that case, diode is in off state. As the capacitor charges to minus Vm, negative peak state, okay, in negative half cycle, the diode is on state at the time. In the consecutive positive half cycle, the capacitor is now charged to M, that means maximum peak voltage, and the diode is in off state and gets open circuit. The output of the circuit at the terminal will be VO equal to Vi plus Vm. Okay, summation of input voltage plus V maximum. Hence, the signal is positively clumped as shown below. Look at over here. You see, the signal is positively clumped. The VO changes according to the changes in Vi, but shifts the level according to the charge on the capacitor as it adds the input Vi. Okay, so this is called positive clumper circuit or positive clumping. Okay. So this is the input, green color, orange color is the output. This is clumped above zero. Case 2, positive clumper with positive reference level. A positive clumper with positive reference level circuit consists of a reverse bias diode in shunt, a capacitor C in series, a reference voltage VR, and a resistor R in shunt as shown in the figure. Okay. This is the reference voltage and this is the resistor in shunt. So positive clumper with positive reference VR. So what do we expect over here? You see, this is the input signal, and above the reference voltage we are getting the inter signal out. You see, our reference voltage, if we give 2 volt, okay, in this case let's say we have 2 volt most likely because it is 2. So above the reference voltage we are getting our inter signal. Okay, so this is the positive clumper with positive reference level. This is a positive reference level. Case 3, positive clumper with a negative reference level. So what we expect? Look at over here. A positive clumper with a positive reference level consists of a reverse bias D in shunt. Okay, this diode D in shunt. A capacitor C in series. This is in series. Reference voltage VR. This is the reference voltage, and a resistor R in shunt. So it is positive clumper with negative reference VR. Positive clumper with negative reference here. Okay, negative reference here. So what we expect? Our entire signal will go down according to the reference voltage. Look at over here. This is our input voltage, and you see our signal is going down according to the reference voltage on the negative direction because this is negative reference level. Okay. Case 4, negative clumper. When a positive peak of the signal is clumped below the zero, then the signal is said to be negatively clumped and the circuit is said to be a negative clumper circuit. So look at over here. This is our input signal. This is our circuit diagram. Okay. This is our input signal, and this is inter signal is coming below zero. Okay, negative Clumpert circuit. Now, case 5, negative Clumpert with positive reference VR. So this is the positive reference VR and negative Clumpert circuit. So what will happen? This is the positive reference. So it will not go entirely below 0 because there is a positive reference. So below the reference value, the signal enters signal. Okay. This is the negative Clumpert with negative reference level. So in this case, certainly you can guess this is our circuit diagram, this is our input signal, and you see our reference level is negative -2 over here. So entire signal is going below it, negative reference level. This is our input signal, blue color. This is our negative reference -2, and our signal is shifted down below the negative reference -2. So let's go for a small test. A Clumpert circuit is also called as a option 1, 2, 3, and 4. Which one is true? Fallen asleep? Give me feedback. Otherwise, I feel that you are sleeping. Clumpert circuit, it shifts the level, right? It does not limit. It does not shift the amplitude. It does not slice. It levels the shift. It shifts the level actually. It shifts the level. That is level shifter. Okay. Next, a positive Clumpert circuit consists of in series some one element series and two other element shunt. Which one is true? A, B, C, or D? Option A, B, C, or D? Which one? This one. D. Let me check. No. B. No. The 50-50 chance. A or C? Option A or option C? First one or third one? Yes. A positive Clumpert circuit consists of a capacitor in series, reverse bias diode D, and a resistor in shunt. Okay. Last one. The Clumpert circuit can clamp at two different levels. True or false? At the same time, we can go up and down. Yes. So I think your quiz is somewhat okay. 2 out of 3 have done. But you need to get 3 out of 3, okay? Now is the simulation. 6 options for the simulation. First one, positive Clumpert circuit. And this is the instruction. What is the instruction? Observe the circuit diagram of the full wave rectifier. Click on the power button. Select the amplitude of the input signal Vi. Select the frequency f of the input signal Vi. Then select the channel 1 to observe the input signal on the graph. Then select the channel 2 to observe the rectified output. Select the dual to observe the both input and output signal on the same graph. Change the value of A Okay, that means the amplitude of the input voltage to observe the variation in the input and output signal. Step 9, hover the graph to observe the value of Vi and Vo at the instant of time t. Save the graph if you are done with your experiment. And this is the note of the experiment. Ideal diode is considered. Make sure always inputs and amplitude is greater than 0 volt. Make sure always input signal frequency greater than 0 hertz. Load resistance are equal to 1 kilo ohm. Scroll on the knob to vary the value. Let's see. So this is our circuit, positive Plankford circuit, a capacitor in series, diode in shunt, okay, diode, forward bias diode, right? Is the diode forward bias or reverse biased? Who can tell? A positive bias consists of capacitor is a reverse bias diode in shunt. Okay, reverse bias diode in shunt and a resistor R in shunt. Okay, so that's reverse bias diode. Okay, this is reverse bias diode. So let's give the power. Okay, now applied voltage V is 5 volt, this is 5 hertz. Let's see the channel 1. Okay, let's change the amplitude according to the requirement. Don't make it 0. Okay, so that's the input signal. Now see the output, channel 2. You see, it is shifted above the reference voltage. You see, positive Clamper circuit. Entire signal is going to the positive direction. Look at the orange color, shifted high above 0. Positive Clamper circuit. You can just change the frequency to like. Change the amplitude. Okay. So it is a positive Clamper circuit, and as suspected, our entire signal is shifted above 0 value. Okay. Next, positive Clamper circuit with positive reference. Okay. So we give a positive reference here. Over here, let's turn on the power. Same circuit but with a positive reference, and what we see as suspected, the signal has been shifted above the positive reference voltage. Look at over here. Positive reference voltage is 3. So our signal is shifted above 5 plus 3, I think. 5 plus 3. 8. Look at the voltage level over here. 10. 5. Okay, our reference voltage we are giving 5 volt, not 3, okay? 5 volt. So 5 plus 4, that the reference voltage is just add it. 5 plus 2 is 8. Now look at over here. 5 plus 3 at position 8. You see? Shifted at position 8, okay? So if you change, just add these two. Vi plus Vi reference, this one. You see, if you make it, let's say 4, 5 plus 4 is 9. So you see, this point is 9. This point is 9. Okay, so make it, change it to, let's say 6 plus 4, 10. 6 plus 4, so this has moved to 10. Okay, so just add the reference voltage, because this is ideal operation. 4 reference battery, the reference voltage plus the amplitude of the signal. 6 plus 4 is 10. So you'll see this one is at 10. And intersignal is above the reference voltage. Reference voltage is 5. If we change the reference voltage is 4 over here, okay, not 5. If we change it to 5, you see, then you see, above 5 the intersignal appears. This is 5 reference voltage. So if I change the reference voltage to 1, then above 1 volt. Okay, so we are clumping depending on the reference voltage plus the magnitude. Okay, 7 plus 1 is 8. So you see this is 0.8. This is 0.8. Okay. So let's turn off the power. Positive clumper circuit with a negative reference. Okay. So this is our circuit. This is a negative reference. So we'll see that our output will go below the reference voltage. So let's turn on the power. Positive clumper with the negative. So below the negative, I think above the negative voltage, it will pull the entire wave shape down, okay, according to the reference value. So this is 7 minus reference is 1. Okay, if it is 7 minus reference gets 3. 7 minus 3 at 4 volt location we will get the signal. Look at over here. The signal is at 4 volt. Orange color at 4 volt location. This is at 4 volt. At 4 volt location, that's the signal. Okay. Because 7 minus 3 is 4. So the signal will go up from 0 to 4 volt up, okay? Because magnitude is 7 volt, negative reference is 3 volt, 8 minus in this case 5 volt. We see, you see, our output is start from 5 volt. Okay, there are some construction work going on. So this is the positive clumper circuit with the negative reference. Now see the negative clumper circuit. So what do you expect? The signal will go below 0. Over here, this is input 5, you can see 3, channel 1, channel 2, you see entire output has come below 0. This is the one. So this is the negative clumper circuit. The negative clumper circuit with a positive reference. So in this case, it will go to the negative direction, but it will add the reference voltage with it. So let's see, power on. Look at over here. Our reference voltage is 3. This is the reference voltage 3. Okay, reference voltage 3. This is the reference voltage. So it's supposed to go down below 0. So instead of going down below 0, what is happening? It will go up 3. So you see some portion. Okay, it is 3, I think. Up 3. You can go up 3. So at level 2, you see this is 2. It's supposed to go at this location 0. Okay, but because of reference voltage up 3, just shifted up 3 volt up. Okay, shifted 3 volt up. So let's change the value of reference voltage to 4. Now you see it has been shifted up value 4 from the 0 reference. Okay, so that's the negative clumper circuit with positive reference, and the negative clumper circuit with negative reference. So negative reference means again it will go below the reference value. It will go in the negative direction plus the reference. Okay, let's power it on. Our negative reference is 4, so we need to count from 0 to 4. So minus 4 it will start. Channel 2. You see minus 4 it is started. Channel 1 is the input voltage. From minus 4 our output will start. Minus 4 to 1. We start from minus 4. So you can just change the value. So if you go to the reference voltage 3 volt, so 7 minus 3, 4. So what happens? 7 volt we are applying maximum amplitude, and battery voltage is 3 volt. So it's supposed to go below 0. Instead of going below 0, it is I think minus 3. That means this is the reference voltage. This voltage it is going more below minus 3. Okay, so it's a negative reference. Negative number circuit with a negative reference. You can just change the value and see the effect. You see? So that's the last one of the clamping circuit. Next, I think we'll go for the post quiz. Identify the below input to output curve of a clamper circuit. This is the input, this is the output. Which one? Negative clamper, positive clamper with a positive reference level, negative clamper with a positive reference level. Which one is true? Which one is true? Give me your feedback. Positive clamper or negative clamper? Yes. Good. Now, Identify the input and output curve for the given circuit. Positive clumper with positive reference here. This is the reference voltage, and this is the above the reference voltage. So it looks like option 2, right? Option 1, option 2, option 3. Positive clumper, okay, with a positive reference here. So this is the positive reference here. I think it looks like this one. Okay. Next, identify the input and output curve for the given circuit. Negative clumper with negative reference here. Negative reference and negative clumper will go below 0 and plus the negative reference. So most likely this one is the right one. Do you agree? Yes. Done. So we have successfully completed the clumper circuit and clipper circuit.